All right, welcome back, and thanks for staying with us or joining us. Our next talk will be from Goswin Rothenthal. So welcome, Goswin. Hello, how are you?
Hello, Thomas. Can you hear me?
I can hear you fine.
Great.
So you're going to talk. I think you're one of the really interesting people here because your background is definitely not a software development.
No, it's not.
So what do you do?
Well, that is actually already my first slide. I'm an architect.
All right. So we're going to learn more about that when you start. One last question: Where are you actually now, right now, at the moment?
Right now, I'm in Vienna in my office, and it's 8 o'clock, so it's nice and empty by now.
Okay, so it's 8 o'clock in the evening in Vienna, and we're ready for our next talk from Goswin. So I think we're ready. If you can start the screen sharing, then we can get started, and people can learn more about you and your work, which I think is pretty amazing.
Okay, let me get my screen shared.
Very well. So now we can still see you, and hopefully we'll get the screen there in a second. I think in Skype is that little plus button.
Do you have the screen?
Now we're almost there. Yep, and there it is. Yep. We can see your screen. I'm gonna put it on full screen here.
Great.
And there we go.
So
yep.
You see my screen?
We can see your screen. Everything good?
Right.
You're ready to go.
Great. So as Thomas mentioned before, my background is architecture and not computer science or software. But I worked for 6 years in London at Zaha Hadid Architects. And the geometries we were working with were very complicated, and we had to build them. And also this project in Macau, and we needed to use software in order to manage our geometries. So for parametric models like this, the most common tool is RhinoScript, which is based on VB script, and it's hosted inside the Rhino 3D modeling tool. So you will see that in the end. My talk shows you first the Louvre Abu Dhabi project for about 15 minutes, and then I will swap to actually a little demonstration. So now I'm working at Wagner Bureau. Wagner Bureau is a specialist contractor for complicated steel and glass structures. We have done building like the Reichstag in Berlin, or the tip of the Swiss Re building in London, or the courtyard of the British Museum. The project I'm talking about today is the Louvre Abu Dhabi. It is a project designed by Jean Nouvel, an architect from Paris. Like with many projects, there's usually a lot of companies involved. So our main client was TDIC. The project manager was managing company was Turner. The architect, as I said, Jean Nouvel. The design engineer and the supervising engineer was Bureau Happold from London and Bath. The main contractor was a joint venture from Arabtech, San Jose, and Auger. And Wagner Bureau was the subcontractor for the steel and aluminum cladding parts. So this is how the development of Saadiyat Island is intended to look when it's done. Here you see the current screenshot from Google Earth. I'm pointing to the Louvre Abu Dhabi here. This state is already a few months old. This shows the concept from Jean Nouvel. He wanted to have several museum pavilions below a gigantic dome that is shading those museum pavilions. So you can see here below the museum pavilions, and on top of that, a dome. The dome is not watertight, it just provides shadow, and it draws a pattern through these shading layers. There are 4 layers on the outer side and 4 layers on the inner side. In between is a steel framework. The steel framework itself is already very complicated, and it's only held up on 4 corners. but I'm going to be talking only about the cladding layers today. Here you see this pattern as it was imagined by Jean Nouvel and the play of sunlight coming through, drawing a pattern on the floor. He calls it the rain of light. So let's go to the engineering. The geometry of the dome is actually relatively simple. It's based on a sphere with regular planes cutting through it. So there are these planes cutting through the segment of a sphere, and these cutting patterns run in both x and y directions. The result is an underlaying grid that you can see here. So this underlaying grid is nice and square in the center, but it's actually distorted towards the edge. That means since we are orienting our pattern along, can you hear me? Good. I have some background noise, a bit strange. Okay, good.
You can ignore the background noise.
So this this pattern is not regular, and that's why we have all the elements of our cladding are gradually transforming, and none of them are identical, even though they look very similar. So here you see four of the four cladding layers. These four cladding layers have a different scaling, they have a different density, and they have a different rotation to create this intrinsic pattern that you have seen before. The different density was derived in various lighting studies that were done by Jean Nouvel, Biro Happold, and Transsolar. The concept was to provide the museum's buildings with a maximum amount of daylight onto the glass roof, while the water and the public plaza area should be in a shadow. So they made some intensive lighting studies, and the result was a bitmap that defines the density of the light from 8 to 0%, ideally. This is what we then translated into our geometry, where we defined these star elements, as we call them, with various sizes. Also here you can see how the density of the dome in the center is less than on the edges. So this slide actually shows very well the principle of the unit that we used for installation. We called it a star. One star can be composed out of several aluminum profiles that are clipped together, and they have various sizes depending on the shading requirement, whether it's small, we use the slim star, or whether we have want to have it rather dark below, then we use the white star. And in the transition zones, the star have a mixed combination of profiles. You can see here a sketch of how these aluminum profiles are clipped together. In total, one star is made up to 120 individual cut profiles that are clipped together. You can see here how they are arranged and numbered. And we obviously needed to cut them at the end and cut them to the right size. So this here is already jumping very quickly deep into details. You can see a system drawing of how these profiles are cut at the end. They have different angles, they have different drilling holes for the corner connectors, and they have some interior slots to accommodate some end plate structures. But so in order to define all of these profiles, and in total we have almost 500,000 of aluminum profiles that needed to be cut, we didn't make a drawing for every profile. We just defined variables like the total net length, the amount of drilled holes, the slots, and the angle. And then from these angles, variables, we directly controlled, or our manufacturer directly controlled the CNC cutting machines. So this was the derived data. For each line represents one profile with all the values that need to be taken in consideration for the CNC milling. In total, this was 460,000 lines of individual elements. This is now how one of these aluminum profiles looks when they come out of the extrusions. And this is one of the machines that was used to cut the profiles and mill the holes in the end. Here you can see one of the initial profiles being cross-checked with the list if everything was done correctly. Then there was a relatively detailed assembly instructions for how to a clear sequence of how these elements with the corner connectors have to be put together. Here you can see again the individual elements that make up one star, and here how they are clipped together. Here again an example of the profiles clipped together. This end profile will be covered with an end plate. This is another image from the workshop where you can see the profiles. There was obviously a lot of logistics involved in storing the profiles before they could all be assembled after being cut, and a lot of manual work in assembling those profiles to stars. For every star, we had a drawing to not only check the dimensions, but to also see where we have to install the connectors that you see marked here with little circles. These connectors are connecting the stars to each other and are holding the structure together. You can see there in total 7,850 stars. So we have a drawing for the top and a drawing for the bottom side. So in total we have 17,500 drawings. These drawings were actually printed and used on site. These drawings, as you see them, were all generated in the software, in the CAD software Rhino, and our script that was driving it was written in F#. That also includes the QR code that you see here that we used later for tracking them. Now I show you part of my 3D model. What you see here in the 3D model is more of a visualization than the actual information that we used for fabrication, but it helped to understand the system. So what you see is the underlying steel structure of the steel space frame, the top chart. And there we have to install the posts. These posts are derived from intersecting the positions of the cladding with the axis of the underlying steel. On top of this first layer of cladding is another series of connectors that are holding the next layer. On top of that layer, another series of connectors. And all of this position of these connectors was predefined on the drawings that you have seen before. So these drawings already defined where these connectors are sitting, and we could deliver the stars with all the connectors pre-installed. So another layer of connectors and another layer, and this is the last layer of cladding on top of that. Here you see some details at the end of one of these profiles, or here as well. This image shows our naming concept. So together with the parametric model, which was based on the half-edge data structure, we also included naming that followed that principle. This is a partial model where you can see the underlying steel structure and several layers of cladding incrementally added. Now we're already on site. This is the steel structure going up here as well. This is one of the first cladding stars installed. These cladding elements have still a protective plastic foil on them that will be removed in the end. This is more into the project of the cladding elements. Here the dome is almost done. Some views from the interior where the cladding elements have already been cleaned. Also here. This is some support towers that are currently being dismantled. You see in the background how the light is shining through those cladding stars. By now, the dome is actually completed, and we're only doing some quality checking. This is on the inside again. This is one star element before it gets lifted up. And the completed dome here. You can find more images on this website from thenational.ae. As you have seen, many images of most of the recent ones I've been taking from there. So how about F#? I used F# in Visual Studio for the main logic and the main data structure, for the core and for the comprehensive, for generating the lists. And I used Rhino for hosting the F# and to actually draw geometry and to save drawings and to turn around my 3D model. And Tsunami is a nice F# editor that can be hosted inside Rhino to generate to draw elements, because it's not possible to draw in Rhino directly from Visual Studio. It needs to be hosted inside Rhino. So now I want to explain you the data structure of the cladding elements. I have drawn here them on a grid. And what you see here is really the core elements that define the grid, and that what I used to define this grid. And I'm not only taking the star element itself, I'm also describing I think you see my mouse pointer. I'm also using the octagon here as an element in my data structure in order to be able to do offsets here inside this octagon and inside the triangle and inside this quadrilateral face here. So what I did is I describe these, I consider each of these, this octagon, the 4 triangles and the square in the center as faces that have continuous points around it. So that's what I described down here. You can see in the beginning the octagon, 4 triangles, and in the end you can see the last face, the square in the center. And I described them here just by X and Y coordinate. And what you see here actually is already F# code as I have written it here. It doesn't need to be much more complicated. And you will see now how I'm taking this little description of the pattern into Rhino, and I will actually be generating this single element. Okay, so let's see it live. Are you still hearing me, Thomas?
Hear you, and now we can see your 3D model starting.
Okay.
With Tsunami on the side.
Exactly. So this here is my I can shut down. This is my the Rhino 3D modeling environment. Anyone who wants to test this can download it, a 90-day trial for free. It's fully functional. So they're very Rhino is very generous for testing, and student licenses are actually very cheap also. And Tsunami installation by default comes with a Rhino plugin. So you just need to drag and drop that plugin once into Rhino, and then you can load Tsunami by just typing Tsunami here in the command line, like this. Okay, so let's go to our grid. So this pattern that I've shown you and the definition of one element, you can see it now here in defined as an array of arrays in F#. So let me reset this here first. So first I just load this by just pressing Alt and Enter. And now I have my array of arrays defined. Here I have a tuple of integers. So in order to work with this array, I create a little function that maps onto arrays of arrays. So I will use this little this inverse pipe operator to create that function. You can see now this function is defined as arrays of array of A to arrays of array of B. So now I have the mapping function that I will be using always to iterate over this pattern here. Next, I'm referencing the Rhino DLL and opening the Rhino geometry namespace. So far you don't see anything. And I will convert now these tuples of integers into actually 3D points. So this 3D point is defined in Rhino in the namespace I just opened. I convert the U and V value to float, and the Z value will be just 0. Now, as you can see here, I have now this array of points. You still don't see them. And I could now actually draw these points, but I would be more interested in drawing the lines. So I'm creating an array of lines where I'm always using this element and the element afterwards. So I'm first taking the index, and then I'm iterating through this array here, taking always the element and the next one to create a line instance. A line is just defined as 2 points. And last, I create connect the last with the first element here in this pattern. So now I've created all these line instances. You still don't see them. And now I'm actually going to draw them. So I'm going to reference the current document of Rhino. And then I'm using the map function that I defined before to add these lines. And then in the end, I'm going to redraw my view. So this is now drawing this pattern here. You think that's a lot of effort. It could maybe be done simpler, but the way I build it up, I can work from here on, and I still have all these points in the sequence, and I will be laterly able to add them to a data structure that represents each of the faces as a circular element. So in order to now extend the grid, I'm going to define a little function that shifts these lines around. So this is here my shift line function. It takes a tuple of the X and Y offset and a line, and it constructs a new line where it adds the offsets. And how often do I want to do this? Let's just do it once. It's always 6 steps, because 6 steps is the unit from here to here. The distance from here to here is 6 units. So that's why I need to always shift it by at minimum 6. So I shift it from -6 to +6. This is my new grid. Then I'm going to map this grid onto the lines. And in the end, I draw it. Oopsala. Something went wrong here. Shouldn't have the Y. Obviously, I have to add the Y offset to the Y coordinate. Let me delete this. So I run this whole block again. And now you see how the grid gets generated. I'm gonna make this grid a little bit bigger by putting a higher value here. Let's do 8 units in both directions, and I redraw this. And now you see how this grid is generated. And when you click on these elements here, you will notice that they're actually always two, because they're pointing in opposite direction. One line points in this direction, while the other line points in the other direction. One of these lines belongs to this octagon, and the other line belongs to the triangle here. That's why I